Welcome to everybody. I'm Luboš Šebatka from IDRS, and we are developers and maybe we can say inventors of new software for connection design. I am very pleased that you are interested in our connection design, and I like to show you some features, and we can discuss, or I can answer our questions, and I can explain what you want. I have three parts of my presentation. First is I show you some examples which we are able to calculate or analyze. Then I have some PowerPoint where I can explain also the background of this software and the project where we developed it. And finally, I show some complex join with spliced plates. So this is our demo project with more connections in one project. In our software, we can solve more connections in one project. It's not only for one. So here is such complex joint with column, with end plate. There is the one beam with shifted end plates. There is also another one with short end plate. There are some openings, stiffeners, etc., etc. So quite complex joint. We can solve base plates, anchoring. So this is a simple typical example. Of course, we can have reinforced base plates. This one you already saw. These shifted end plates are quite interesting for connections with bending moment on the weak axis of another beam. We can make welded joints from open sections. We can do such things like end plates which are welded. We can solve 3D joints with like here you can see with openings if there is some necessity to put a pipeline here. We have such typical examples like this column with end plate with hinges. Another kind of base plate. What is interesting is that we can combine also for base plates, combine more elements or more members in one joint. So you can see that there is interaction of column and interaction of diagonal from the bracing, and we can solve it together. It is quite important because this if you calculate it like that, the situation can be worse, but it can be also better. For instance, here this gusset plate in fact works like stiffener of the base plate. So if we connect this one more member to connection, in fact we can help and the connection, and we can make the more efficient design. We can have also apply this splice plates, splice connections with huge groups of bolts. This is quite interesting connection. It's for tower masts, big calculated big and complex gusset plates. such cassette plates normally are only estimated, or you have to calculate it in some program like ANSYS or something like that. Our goal is to solve such things in our program in easy way, and you can see that there is no necessity to estimate anymore. We can simply calculate it. Here you can see stresses in all parts of the connection. So also these complex members we can efficiently design. In this part, I show you also how we work with templates. You could see that we are able to resolve quite complex connections, but our program is also for simply ones. For instance, such connection is not difficult. All other software solutions on the market are able to calculate such things. So our goal is to do it also in some easy way, and for this we can have templates. Any connection which you design, you can save as template, and again you can use it as template, apply template. We recognize the shape of the connection, and program offers the number of possible solutions of these connections. Like here it is a welded connection, this is welded with end plate, this is bolted connections with end plate, this is connection with hinge, this is this stub of when the bolted end plates are moved from the connection. It's done also very frequently. We can have also the simple connections like on thin plate, or such connection with double hinges. If you find the template which you like, you say only apply, and the connection is constructed, and we can calculate it. So we have this connection, or we can delete all and use another one. Apply template, maybe this step. Yeah. So on this I want to demonstrate that we are able to solve the general shapes of connections, but we are quite efficient also in design of typical connections. So in the second part I would like to tell you something more about the background of the program, and things a little bit more about theory. If you have any questions, please ask immediately. I can react and explain. So this is my presentation which I normally use. I do it a little bit more briefly, and show at the end I show you some live demo how to construct complex connections. This is the range of joints which we are able to solve: open sections, closed sections, welded, bolted, with stiffeners, hinges, etc., etc. These stubs like this, gusset plates, untypical, not typical. Base plates, this we already saw, this we also already saw. Our software was invented in the team of which is composed from our company and people from universities. We for several years we prepare it, especially with Professor Wald from Prague University. We had a dream to calculate, to come with general solutions for connections. And 2 years ago we got the governmental grant from Technological Agency of Czech Republic. So we started in this question if it is possible to analyze steel joint with precise and general way. We composed this team from these two universities, Prague, Brno, and from our company. And we started, in fact, in January 2013, and the first release we had in the middle of this year. This is about our company and me. So the goal of the whole project is to come with a general method for connection, with method which is simple and fast, and the speed is competitive with existing solutions, and the method which is comprehensible. So it means that structural engineer get the information what is happening in the connection, where are the high stresses, how the bolts are loaded, and etc. etc. We think that the current methods are not so explanatory, that users only fill some formulas and get some results, but the real understanding what is the weakest part of the connection is not here. And so we develop new software, but we had to invent it new design method, and this method we called component-based finite element model. This name was invented by Professor Wald. Anyway, Professor Wald is in fact one of two authors of Eurocode of part of Eurocode for steel connections. Professor Jaspar from Liège and Professor Wald from Prague are the main authors of connections in Eurocode. What is important to say is that we do not want to say that the current component method is wrong. It's completely not our goal. Our component method is very good, is safe, it gives efficient design of connections, but is not general enough. And what we did is that we combined the best parts from component method and best parts of finite element analysis. And some solutions are so unique that we apply for patent protection of that. Normally I explain this method on several examples, or I say stories. So I briefly go through of all of them. The first one we call reinforcing too late. It is based on a real example from my life. Several years ago, one friend of mine came to me with such detail of cord of truss girder, where is the change of profile depth. It was a big factory where they designed a lot of truss girders, and when everything was finished and the factory started to produce cars, the investor said, I don't like this detail and do not trust in this detail, please prove that it is safe. And this guy came to us. We make this model in C Engineer at that time. We calculated in with elastic material, and you know that you get some peak values, and there were stresses 600 megapascals, and all of us know that it is nonsense. It cannot be in the steel because steel is plastic material, but we had this precise model. We were not able to say the detail is safe or not safe. Yeah, so we made some stiffening of these nodes, but really only it was our estimation. No real analysis. So the first thing what we realized is that if we calculate connections, we have to calculate with nonlinear material, is linear and plastic. And when we apply this approach, we cannot make checks on the stress, because stress is limited, but yield stress, and we have to make checks on equivalent plastic strain. And according to Eurocode, it is recommended that the strain should not exceed 5%. So this we use in our software.
Can I ask something?
Mm-hmm.
Can I ask something? Because I wondered whether strain hardening is taken into account in calculations.
No, we use this this diagram in fact with horizontal part of this plastic branch, but from the practical reasons of stability of the solution, we have it not completely horizontally, but there is very
1% or something like that.
Something like that, very low, because this method, then the iteration is much faster, and the solution is stable.
Okay. Yeah.
And now we have results from our software. This is the solution what were there, and really you can see this is this comprehensive result. You can directly see that the detail was really wrongly designed and was dangerous for the building, and the equivalent stress was 20%. And we can analyze such connection, such node. We add, for instance, here very small haunch, but even this small haunch really helped. And in fact, this design is good enough. But you can make even better with the stiffeners in the direction of top flange of this beam, and such design is perfect. So the second one is another story. Another friend of mine, the president of Czech Association of Steel Engineers, came to me several years, asked, I have this connection on some huge bracing diagonals, which big normal force, and he said, I'm able to calculate this connection, but I do not want to have these boards, because I think they are useless. They are only additional costs, and they do not help the connection, and I want this. And again, we were not able with current tools calculate such group of boards. Now we can, and we have some editor of boards, so you can start with this regular group, and then delete the boards which you do not want to have. And because we calculate with finite elements, we can do, in fact, general layout of bolts.
Can I ask something again?
Yes.
About the several things. The bolt hole diameter. It's always just fitting a hole indicated in the picture to the right. So when it's bolt M24, there are always holes 24 millimeters. But
yeah.
at least in these overviews, in these drawings. But how is that taken into account in the bearing calculations? And so there.
I will explain later. It is in my presentation, but you are right. This value is wrong. There is we should change it. There is diameter of bolt, not diameter of bore hole.
And then another question: the shear force when I want to see the bolt forces, as I can see here, are the normal tensional forces. But I wondered the distribution of the shear forces in these connections. Is there? How can I see that in the graphical overviews, or is it at least possible to say to the software, I want you to place the shear force to, say, the lowest row of bolts, because that's the distribution I, as a designer, have in mind when making my hand calculation. Is that possibility present?
We have this possibility to show, and I show it also. Yeah.
Okay.
A little later. But it's a very good question. Thank you. I only here you can see that these boards are really useless in the design, and you can design any shape of boards, any shape of group of boards, and we can make this design. Again, a little bit more theory. Sorry for this Czech text. We have bolted connections in the model, and in fact, bolted connection is the contact between two plates. For contact, we have this diagram where in pressure the contact is in action, and in tension the contact is opened, like here. And there are bolts which are modeled like these nonlinear springs. We started in the beginning with only the elastic branch of bolts, but we did not get good results for bigger groups of bolts. So finally we invented this diagram where the initial elastic part, and then is again not horizontal but this plastic branch, and this is derived from results from tests of bolts, because the bolt as it is cannot plastify, but things like I do not know this. I don't know this English word. The things like this nut and some parts are really plastic. So this diagram is much better, and the results are satisfactory. We do verification studies like this knee connection. You can see the results calculated by component model, results calculated by SBFM the agreement is less than 5%. The same we have for bolted connections and base plates. This example is a little bit different from this first two one. This was a little bit expert analysis of connections. This is from the opposite side of the spectrum of tasks of structural engineers. It's very simple structure, maybe 2.5 meter span, and it is roof in front of our office. So I see it every day, and I am sure that it was not analyzed. It was not calculated. Only somebody say, I need this haunch, I need this number of bolts, and etc. I do not believe that it was calculated. Because even it is not very important joint, it is quite complex. And here you have one end plate, haunch, there is the welded connection on the opposite side, here are fin plates. So it is not easy to analyze with current tools. We are able to model it, and we are able to analyze it. Here is this initial shape with this haunch, and we tried without this haunch, and you can see the results are still fine. And so we, in this example, we want to say that when we analyze also such things, we can save costs and we can save money, because there is some steel plate, and also the welding in this topology is not very easy. So when we analyze properly, we can save and decrease the price of connections, or we can make different variants of such connection or such joint, and again we can make it simpler and cheaper, like here. Why how we construct the joints. All software on the market work with connection types. In such programs you can have a list of connection types. You can choose one of them and have the solution for this type. We do not do it. We have the general geometry of connection and apply operations or manufacturing operations. In fact, what is really done when they produce the joint in the workshop, we use the same operation for construction of the analysis model. Therefore, we speak about manufacturing operations, and we have a lot of them, like cuts, base plates, wideners, stiffeners, ribs, gusset plates, openings, end plates, and we have now much more of them in the current version of the software. This story is about this base plate. Again, a little bit theory. There is concrete in the joint, and we decided to model the concrete like Winkler-Pasternak subsoil, what is normally used for design of buildings. So if it works for buildings, why it cannot work for connections? So only the stiffness is of the material is different. It's not soil, it is concrete. So we have this one. There is again some contact element between steel plate and concrete, and then we can calculate contact stress between steel and concrete, and we can check this this stress. Anchor bolts are again like bolts like we spoke a couple minutes ago, and we check also shear force, and this shear force in our model can be taken by only by friction, or by shear iron like here, or by flexure or stiffness of flexure stiffness of these anchors. We are also able to take into account the mortar joint. In this example, we wanted to say again that we can solve such typical shapes, but we can solve also untypical shapes if there is not enough place in the building. Then you can really make your design of plate, and we are able to give you results. This is only to show that we made some real tests in lab. It is in Brno University, so there are some pictures from these tests. This story is does everybody really know? In each software you have this option, this type, and they say we are able to design a knee connection. It's true, but with our software we are able to play it. For instance, this position of stiffeners, and they have really remarkable influence into the capacity of the connection. Here we have not stiffed connection. Here we have stiffeners in the direction of flanges. Here is perpendicular stiffener. This one is completely the same as this one, but is in opposite direction. And here we have quite more inclined stiffener. And when we calculate the limit capacity of this these connections, you really see how big is influence of the position of stiffener. I know that it is not very often done, this one, yeah, but it has nice influence and improve the capacity of the joint. Interesting is if you compare this and this, there is completely the same stiffener, same plate, same welds, same price, but the capacity is better. Yeah. So I say on all my presentations, we do not want to teach structural engineers how to design connections. You are clever enough. You are cleverer than us. So we don't want to tell you how to design connections, but we offer you the tool where you can analyze your design, your ideas, your inventions. So this is what we want to do. Again, a little bit more theory. This is the standard component method, which is described in Eurocode and which is normally used, and it is based on such models. In fact, for each topology of connection, you have to derive such model from springs. Each spring represents some component, and you can see that these models are not very easy. Not everybody is able to make such model. And the problem is that for each topology, this model is different. So the method is general, but for each type, you have to derive new analysis model, and this is the problem of this method. And what we when you calculate this model, you get the forces in all these parts, like in bolts, in end plates, in flanges, etc. And for each this force, you can make the check according to Eurocode. Yeah? Each component is checked according to special formulas, which are described in books and in Eurocode. And what we did is that instead of this complex spring model, we use standard finite element model. Everybody use this finite elements for design of buildings, so why not to use it for design of connections? And so we calculate stresses and internal forces in this finite element model, and then we apply the same checks as in a component method, the same checks which are in Eurocode. So it is not replacing of component method, but it is a synergy of component method and finite element method. This is about how we do the meshing. Important is that the user is not working with this finite element model. This is done automatically. All plates are meshed. All plates are connected by welds. The bolts are introduced with some special springs, and everything is done automatically. Now we have maybe answer to your question about bolts in shear. We put bore holes in our model in plates. The bore holes are as the real diameter as according to databases and codes. And what we do here is that we have special model which can transfer the shear force from the theoretical point of bolt to the edge of borehole, and we use again some contact elements here, and you see that the force is really put only the part where the bolt is pressurized into the material of the plate. Yeah. So this plate is in tension, and you see here that all pressure is on this part of borehole. Here it is a little bit different because there is higher stress in other parts of the plate, and here you can see the critical cut which appears in this plate. So the shear is calculated with this special model with contact elements, and we also do special mesh around boreholes. And you can see here that around each borehole we have predefined mesh with these specific elements, and it works quite nice. And thanks to it, we are able to calculate also such complex plates. And here you can see this shear forces or influence of shear forces. I call it is our masterpiece, Meisterstück in German. There is the beam which is bended. There is the bending moment. The top plate is in tension, bottom plate is in pressure, and you can see where are bolts working. This is in tension, this is in pressure, and so the stresses in plates are different. Now very fast, it is our output report, which can be done in several levels of detailness. And finally, we say that we calculate everything in 3D, even the model is in one plane. We do 3D model, and we are able to calculate very complex joints like this one, and the results you have in several seconds. And in opposite to these very complex joints, we support the simple ones with the templates which I already showed. This is our offer of things, and this is the end of my presentation. So I can go now to last part of my presentation, and I want to show you, or I prepared the demo how to make such quite complex connection. Yeah, it is about again the column. There is the diagonal, which is loaded by normal force, but also by moment. So it means we have to design the connection to be able to take into account this bending effects. And this is the shape which we want to get. Yeah. And so I click to another another item in the project where is only the geometry and loads, and we can show how to make such complex design of connection. So
can I ask something?
Mm-hmm.
Is it possible to see whether the beginning of the column is on top or at the bottom? Because when I start a new project, it tends to take the top of the column as the beginning. Is that a known issue? Or because I can see it, I cannot see it in the visual display or in any tables. So.
Mm-hmm. You can see it only here where this pitch is 90%. It means it goes up. If it is minus, it goes down.
Oh, okay. Yes. Yes. So that's this is the place where I can. Okay. Yeah.
And then on the bottom we put the support in our model, and the support is shown in red color. So also this can help you to recognize.
Yes. Yes.
Okay. So let's make this design. So we have this manufacturing operations. You can see that now we have more than in the presentation. So we start with cut of B. say it's member B, it's cutted by member C. It's the cut is perpendicular, and maybe there is some offset. Yeah, so this is the first step. Now we need this gusset plate here. So we add. We have here now a general plate, so we can put the plate. The plate, there is the general plate which can be put anywhere in the joint, and you can define it in a coordinate system of joint or in the system of member, like here. And we say it is on member C. It is. There are more options. It can be rip, it can be widener, it can be doubler. We use it as rip, and we have it on this bottom flange. We rotate it at 90 degrees. So we have here, and now we can put we can put dimensions here. Oh, it's 0 is 400 maybe, and this should be done on the opposite side. So maybe here is 25, and this is 0. Yeah, so we have this plate here. It is welded here. You can see weld. And now we continue with construction of the joint. We want to cut this plate. So we have cut, and say we want to cut plate P1. P1 is this one. We want to cut it by member B. And there is some offset. Yeah, we have some offset between here, and the plate is modified. Now we want to add the splice. So we can have splice plate, put it on B, on top flange. We start with top flange. So we here we define group of bolts. Maybe like that, doesn't matter. So we have bolts on this splice, and now we have to cut the splice by member and weld it, and also we have to resolve this detail, this collision between these two plates. So we continue with cut plate, and we want to cut this splice not by plate, but plate of member, which is member C, bottom flange, and which surface? This opposite surface. We have this. This cut is done, the weld is done. We continue again with cut of splice, and now it is not cut, but it is notch. Yeah, and you can see we have this collision between plate and this splice is done. So this is the new shape of the splice. Everything is welded. It is what we need. And now we do something similar in the bottom, but we make this splice shorter, not to connect it to this column flange. So we can copy this splice plate and say it's not on the top flange but it's on bottom flange, so it is here. And the final operation will be that we cut this plate 1 by this splice and weld it. So this one, it's cut off splice 2. No, it is cut off of plate P1 by splice 2. Yeah, and it is done. So you can try to calculate. And we have results. So quite complex connections. Connection, you can see how we can do it. And you had this question about shear forces. Like here, there is this splice element on splice plate on the bottom flange of the beam. You can see it here with a little bit with this outline highlighted, and you can see it in detail when we switch on bolt forces. You can see normal forces in this view, but you can see the shear forces in this detail view. And here you can have tooltips about sizes of these forces, and you can see that here we have these six bolts. And you can see that the distribution of shear forces is really, in fact, it's like in average value. If you divide the force by 6, you have 16, 15. It's almost 16 everything. So these values are calculated thanks to these contact elements and thanks to this our special model around the boreholes. The results of shear forces are quite nice, I would say.